Here we see or compare the different shift keying schemes, analog shift keying schemes. So the first one is amplitude shift keying. So amplitude shift keying tends to be quite inefficient in terms of occupying bandwidth, and used when we have a very low data rate and a very large bandwidth like optical fiber. Frequency shift keying used in telephone systems, coaxial cable, receiving cable TV, and some radio systems. You can have more than two frequency levels. We used binary frequency shift keying B for base 2 levels, so we can add more than two frequencies, 2 to 4, and goes up to higher. So we have a high data rate but high chance of errors as the number of levels goes up. So frequency shift keying, it is commonly used in wireless systems and combined with amplitude shift keying. It is called quadrature amplitude modulation, QAM. It is specially used in ADSL and some wireless systems. So your ADSL modem, it takes your computer digital data and send it as analog signal. And how does it map the bits is to analog signal is using the combination of amplitude and phase shift keying. So here are some example technologies used nowadays in this shift keying: analog shift keying, amplitude shift keying in optical fiber, RFID, frequency shift keying in the radio communication systems, RFID, in television receiving TV signals, phase shift keying and quadrature amplitude modulations in telephone systems, mobile phone, Wi-Fi cable modems, DSL, and this ADSL modems. So the third group in signal encoding techniques is sending analog data in a form of digital signals. So analog data is transmitted using digital signals, and in fact what we are going to do is we take the analog data and convert it into digital data and transmit into a form of digital signal. So we have two options. The first one is convert the analog data to digital data and transmit it into digital signal as a digital signal using the non-return to zero level. The first part, that is by taking 0 as a low or a high voltage level and bit 1 as a high or low voltage level. Then the second option is convert the analog data into digital data, then send this digital data as a form of analog signal in phase shift keying, which is commonly used in communication systems to treat everything as digital data, even it starts off analog. So we have to make it everything digital, so we change analog data into digital data. So here we will going to see how to digitize this analog data. So we have a device called codec that converts this analog data into digital data and recovers this digital data from the analog data at the receiver end. So the conversion is called encoding and the recovering is called decoding. So the two are called codec. So there are different type of techniques used in analog data to digital data conversion. So we will see in this class the pulse code modulations and the delta modulation. We will see it in the next in the higher class. So let's look at this pulse code modulation by example, using this example. So here we see this. Think of this a solid line curve is our analog data. So it is a representation of our someone voice or recording music or a voice. This is our data that we're going to send in our communication system. So what we are going to do is we have a sampling interval time in the horizontal axis, and we have a vertical axis, the amplitude, the signal strength. As we talk over time, the strength of the data it goes up and down, so it is a continuous sinusoid signal, analog data. So this is what the plot is about. So we take a small portion sample interval at a specific time. When we match that interval into the corresponding palm value, so in the vertical axis we divide it into voltage levels, different voltage levels. This is for our analog data, so we divide it into 60 levels. Then this is the corresponding code number, palm value. Then we match using our sample interval. Then we convert that amplitude value, signal strength amplitude value into binary. So for example, here we take as 0, so it falls on the 1 corresponding palm value 1 level, so we change that one into 0001. So the number of bits is 4 because we have used 60 levels. So in order to match 60 levels, that is M, capital M is 16, we'll use 4 bits to the power of n is equal to m. So to find n number of bits, we'll make it we will get 4 bits to represent our 60 levels. Then for example, the second sample interval is here, so this magnitude value is falls into corresponding palm value 9, so we change that 9 into a binary 1001. So we can continue changing the pulse amplitude modulation value into binary. Then this will be our code, or pulse code modulation code, or digital code, digital number of sequence of bits for this analog data. So let's see another example in this pulse code modulation. So here we have a time in milliseconds, so this is sampling interval time, and this is our continuously varying analog data, and we have amplitude. So first what we are going to do is we have to divide into different levels, so to match to the corresponding palm value. So we divide it into 8 levels, the minimum level 0 and the maximum 8, 0 up to 8. So capital M is 8 levels, and we take a 4 millisecond sampling interval for this mapping or conversion of our analog data into digital data. So then what we are going to do is, for the first one, we match it, or we find the magnitude of this analog data. So it falls in the first level, so we change that into binary 001. So we have 8 levels M, so we change it into binary into 3 bits to the power of 3 is 8. Then the next sample interval is given as 4 milliseconds, so we will take a 4 millisecond interval. Then we found the palm value, the corresponding palm value or amplitude value for this magnitude value for this data. Then it falls into 6, so we change that 6 into binary 110. Then we continue doing like that, 8 milliseconds. The next it falls into 3, change it into binary 011. The next one is 12, it is falls into 1, 001. The next one is 16, it corresponds 010. So this PCM code is our digital code for this analog data, 001, 110, 011, 001, 010. So you can reproduce the digital data from the analog data. So here from 0 up to 4 milliseconds, it maintains a constant level of 1. Then after 4 milliseconds it goes into 6, amplitude, magnitude, then it maintains up to 8, then from 8 up to 12 is 3, from 12 up to 16 is 1, from 16 up to 20 will be 2. So this is a representation of our digital data, conversion of analog data into digital. So this is our analog data, and we convert it into this digital form. So this is the first case that we see as an example. So you can continue seeing the two other cases given in this PDF file.